Okay, so let's get ready then. Right, so let's start then. Last time we defined the ramp cohomology for a smooth manifold. Remember? So it was the quotient of the set of closed forms mod exact forms. So if we have a manifold of dimension n, remember, so we have cohomology on degree 0, degree 1, degree 2, all the way up to degree n. So that was the theory that we have. And we also show that if we have a smooth map between manifolds, I have an induced map of cohomology vector spaces. And if that map was an diffeomorphism, we show that the map that we obtain in cohomology is an isomorphism of vector spaces. And the only computation that we have done, we computed the ramp cohomology in degree 0 for any manifold. Remember, given any manifold, you already know what is the cohomology of degree 0. Do you remember the answer?
R to the number of connected components.
Right. So degree 0 cohomology is going to measure how connected is our manifold. If it's connected, I only have R to the 1. And in general, it will be R to the K, where K is the number of connected components. Okay, now for today, we are going to compute the ramp cohomology of the reals. We will do this straightforward, just following the definitions. And later, we are going to develop a theory to compute the cohomology of some other manifolds. And this is something very important, which is called the major Vittori sequence. Maybe you have seen this in algebraic topology. I don't know, but we will see it here. So let's start with this now. So we are interested in the cohomology of the reals as a manifold. Let's recall a few aspects. So the good thing, we have global coordinates in R. The dimension is 1, and we know that it is connected, right? So that's everything clear. So from at least from these two, we have this, and we know that we are missing this one. Okay? So we only need to compute one group. All of the rest, we know them very well. And we will use this fact to compute this. Now, this is a general one form on the reals. So I'm using X is my global coordinate on R. So any one form is of that form. A function times dx. Now, Why is this? Why is alpha a closed form?
Because if we apply D one more time, it vanishes.
Because, again, I didn't hear you very well.
Because if we apply D one more time, it vanishes.
Right. That's correct, Moises, but why is it going to vanish? That's true. If you apply D, it will vanish, but why is that? Anyone? What is this? Right? Dx, which dx is 0. Also, I mean, this is something that you can do. Now, dx times dx equals 0. Right. Now, what else? So from that, you get that alpha is closed. But what else can you argue in a different way? Because by dimension reasons, there are no two forms on R. Or the only two form is the 0 form. By dimension reasons, alpha is a 1 form, this is a 2 form, and by dimension reasons, it has to be 0. Okay? Great. So, any one form is closed. Okay? Now, to compute this, we need to know closed forms and also exact forms. So far, we know that any one form in the reals is closed. So we use calculus, and I consider this form. I'm sorry, this function. The derivative of this is f, right? That means that the differential of the function is the one form alpha. Thus, any closed one form is also exact. Right? So first, any one form in the reals is closed, and we just argue that any closed form is exact. So this is a mistake. That means that the answer is 0. Okay, so is this clear? So now we know the whole cohomology of the reals. In degree 1, we just computed that, which is 0. In degree 0 is R, because it is connected. And for k greater than 1 is 0 by dimension reasons. So we know the cohomology of all of the reals is 0 everywhere except in degree 0, which equals r. Any questions? Okay. Now remember that any open interval is diffeomorphic to the reals. We saw this at the beginning of the course, and I think even you mentioned which function can we use to show that this is diffeomorphic to this. So because the two are diffeomorphic, they have the same cohomology, okay? So you also know the cohomology of any open interval. It is the same as the real numbers. Right. Any questions? Sí.
Hola Andrés, una pregunta rápida. ¿Tú tienes red?
Sí.
¿Y que funciona bien?
Sí. Gracias.
Ok, porque a mí no me está funcionando.
Right. So let's see. Now we're going to go into the theory, and we are going to talk about the major sequence. This is going to be a scheme that is going to help us to compute the cohomology of a huge class of manifolds. Okay, now before moving on, basically, in order to apply the major sequence, we need to know the cohomology of a few spaces. And based on that, we can compute the cohomology of more and more spaces. So far, we have only computed the cohomology of the reals. And from that, we're going to build more and more examples. Great. Now, the major sequence in cohomology is motivated by some concepts in linear algebra. So first, I'm going to talk about linear algebra here. So I'm going to talk about. Ahora sí, tengo que quitarles. Bueno, ahí está. Okay. Consider a collection of vector spaces and linear maps. Okay. The collection of vector spaces, it will be a finite collection or a countable collection. It doesn't matter. We assume that all of the vector spaces are over the same field. For our purposes, let's do it over the reals. So I have a whole collection of vector spaces and linear maps between them. So all of them gives me something like this. I started with B1, but I don't know. So I have that collection of vector spaces and linear maps. And that sequence is going to be called exact if the following holds. At every j, I'm going to look at the following. The image of this map has to agree with the kernel of this map. And that needs to happen at any space like this, okay? So this is what we call an exact sequence. Okay, so at every V, the image agrees with the kernel. Okay, that's the only condition, and this is only concepts of linear algebra. Okay. For instance, let's assume that I have a sequence like this. It is a finite collection of vector spaces, and I know that this is exact. Then in this case, we can say something about the first map and the last map, if the sequence is exact. But before that, let me just mention this. Usually we write 0 for the vector space that has only the 0 vector. Okay? And when I have a linear map like this, there's only one linear map. Which map is that?
Same to 0.
Right. Because it has to be a linear map, so the 0 goes to 0. And what about this map? Which map is that?
Again to 0. The entire stuff.
Right? Constant function, everything to 0, because that's all that we have. So this map and this map, that's what we understand by writing that. We don't say what they are. And so if I have an exact sequence like this, I can say something about F1 and Fn. That is, this map is injective and this one is surjective. Okay? So for instance, because the sequence is exact, it is exact on V1. The image is 0, so that means that the kernel of F1 is only the 0 vector. Hence, it is injective. Now, using exactness on Vn plus 1, the image of Fn has to agree with the kernel of this map. But the kernel of this map is the entire Vn plus 1. So Fn is surjective. Okay? So in an exact sequence that looks like this, when we have a 0 at the beginning and a 0 at the end, we know something about the first two functions. The first one is injective, and the last one is surjective. Okay? Are there any questions or comments on this? Now, have you seen this before?
Something similar in abstract algebra.
Exactly, yes.
Or groups.
Right. In algebraic topology, this type of aspects are fundamental. Now, another observation is if you have an exact sequence, if you compose a map twice, if you move twice by the functions, you go to 0. Okay? Because you have an element here. It maps here. So it is already on the image of this map. So if you apply the next map, has to be 0, right? So applying consecutive maps gives you the 0 map. Now, another important observation is this one. Again, this is so let's see. Here, I don't care if it's a finite sequence. Here, I do care because my observation is the first one and the last one. And on this last observation, it is important that it is a finite sequence. So if I have a finite exact sequence, we have the following relation among the dimension of the vector spaces. The alternating sum of the dimension will give you 0. Okay? So try to prove that. This is linear algebra concepts. So this is a very useful fact about an exact sequence of vector spaces and linear maps. Right? Okay, and I think this is all that we will use about linear algebra. And now we move into manifolds to talk about the Mayer-Vettori sequence. Okay? So that's about it regarding linear maps. So let's move on into manifolds. So let's consider a smooth manifold M and two open sets that cover the manifold M. On the open sets, there's no restriction except that they cover the entire manifold. They have to be open, so U and V are also smooth manifolds. And they have the same dimension as M. So now we have the following manifolds. I have M, we have U, we have V, and also there is another manifold that it will be useful here, which is the intersection of U and V. That's an open set in M, hence a manifold. Okay. So consider the following inclusion maps. The inclusion of U into M, of V into the manifold M, and finally, the inclusion of the intersections to U and to V. So those four maps are smooth maps. They are inclusions. And we have maps of manifolds, C infinity maps. Thus, we have the induced maps either on the grid K differential forms and also in cohomology. For the time being, I will focus on differential forms like this. Okay. Remember that for a map, the induced map in differential forms changes the direction. Okay. And not only that, we have the following, because either one of these maps is the inclusion. The induced map in cohomology corresponds to restriction. I have a differential form on M, and this map corresponds to restricting my differential form on the open set U. Okay? And similarly for the other three maps. They are all restriction maps. Okay? Now, let's fix a degree K, and we will see that we have an exact sequence. So this is an exact sequence. So let's see what this map is. I have a global differential form. I restrict to U and restrict to V. That's the first map. The second map, I have a differential form on U and a differential form on V. So the map consists, okay, alpha, I'm going to restrict it to U intersection V. Beta, I'm also going to restrict it to U intersection V. And then I subtract one from the other. So those are the maps that are involved in this sequence. Now, remember that these are vector spaces. And moreover, they are infinite dimensional vector spaces, okay? And what we are arguing is that we have an exact sequence. Is the proposition clear? Moises? Okay. Now, let's consider the case k equals 0. What are the zero forms?
Definite functions.
Functions on whatever, on M, U, V, whatever. Okay. Now, what is the argument to show that this is an exact sequence? If we look at functions. So let's say we have to show that it is exact here. I know that the image is the zero function. So what I have to do is to find the kernel of this map. I have a function on M. And then I restrict the function on U, and I restrict the function on V. If the function restricted to U is 0, and the function restricted to V is 0, what can you say? about the function, the global function. I have a function on M that restricted on U is 0 and restricted on V is 0. What can you say about the global function?
Then it's 0, right, over.
Why?
M is the union of this.
Right, so here is crucial that M is the union of these open sets, U and V. Okay, very good. So with that, you show that it is a set here. Okay, good. Now, let's show that it is a set here. So take an element here that goes to 0. So you have a function f on U and a function g on V. So think about it. What can you say about this? So f, a function, smooth function, f restricted to the intersection So if it goes to 0, what do you have? Right? So you have two functions that agree on the intersection. What else? So we took an element here that isn't the kernel of this map. I want to show that isn't the image of this map.
And with that terminology, it being in the kernel of the second mapping is that iota u of alpha is equal to iota b of beta, right? So
Wait.
they are like,
Come on, what else?
no, wait a second, I got confused.
So let's see. Salvador, you want to comment more or not?
Ah, yeah, yeah. So in the initial set, they are like the same in both coordinates, right? So that's the
Okay.
image of.
Okay, give me a second. Let's see where we are. We want to prove exactness here, right? So I took an element there that maps to 0, that it is in the kernel. I want to show that it is on the image of this map. Is everyone with me here? Does this make sense or not? So again, let's try to prove that it is exact. Oh, sorry, 0. There. I want to prove that I have two maps on that vector space. I want to prove that the kernel equals the image. That is the image of the map equals the kernel. Okay? And then what we did is we took an element in the kernel. Right? I have an element f comma g that it is in the kernel. That means f restricted to the intersection minus g restricted to the intersection is the 0 function. Okay. So f is identical to g on u intersection v. Now, what we want is that it's in the image of the other map. We look at an element here and we want to show that it is in the image. That is, we want a global function that when restricted to U agrees with F, and when restricted to V agrees with G. This makes sense? Salvador, Moises?
Yes.
Okay, and then what follows? What is the function? I want a global function. How do I define this function?
On U as F, and on B as G.
And why does it make sense? First
Because,
of
Oh, you
all,
saw
because they agree in the function.
right. So this function is well defined. Because U and V are open, F will be smooth. And this is a global function that restricts to F on U and to G on V. So we prove that the image contains the kernel. Remember that this is what? We want to prove the equality of those two sets, and we just show that the kernel is inside the image. The other inclusion is the easy one, right? It follows by an observation that we already made. If you take a function here, f, go here, f restricted to u, f restricted to v. So that's an element in the image. And clearly, that element goes to 0. Okay? So one inclusion is always straightforward. If you look twice, you get 0. The other inclusion is the one that requires more work. So we have proved exactness here and here. It remains to prove exactness here. Is that clear to everyone? So I'm going to take an element that goes to 0, and show that it is in the image, right? And by taking an element that goes to 0, basically what I mean is take any function here, and show that it comes from a function here. Any ideas on that? So you have a smooth function on a small set, which is the intersection. You would like to show that it comes from a function on U and on V. Any ideas on that? So basically what you have to do is the following. You have a function on the intersection. The function on V that you will take is going to be the 0 function. Here, take the 0 function. And here, you need to come up with a function that restricts to this one. Okay? And how do you do that? So you just need to extend the function. You have a function on an open set, and you would like to extend it to a smooth function on U. Okay? So we are not going to go over those details, but let's just comment briefly. What is it that you must do? You have this, a function here. So you have to take the 0 function here, and a function on U and why can you do that? This is an open set. You have a function defined on an open set and you would like to extend it to any function. So you have to extend G to a function G tilde. And this is something that we argued before, how to extend functions. Okay? So I'm not going to go over the details of that, but I will answer any questions that you might have. And this is to prove the last step that we need here. Okay? There. Any questions?
Can we always do this, like extend the function?
Right. This is what we use. Let's say, well, let's do it over the reals. Okay. So. You have the reals make any open interval here. You have a function defined on that open set. And you would like to extend it smoothly. Right? The first thing that you might consider is, well, let me just constant. That is not going to be smooth. That will be continuous. But that's not smooth. So, how can you extend this over the reals? You want to extend that function beyond a comma b. Basically, the whole point is what to do next. Further than that, you don't care. But how do you extend that to a smooth function? So how do you continue here? Let's say there only.
I don't know. I want to say like maybe if we can find a Taylor series nearly.
That could be one way. Yes, but I will be careful about that because remember that you don't have A and you don't have B in the domain. Meaning that maybe very close to A, the radius does not go beyond A, right? No, remember what we talked about? And here is where we use the fact that it is a manifold is second countable or a normal space. Do you remember that we discussed that briefly? So I don't know, Daniel shared with you something about topology and I don't remember what was exactly. He shared some notes regarding topology. But basically the way to extend this relies on, for a manifold, in terms of topology. So let's say, maybe you can talk about a bump function, right? So you have a bump function here and here. If you have a bump function here, do you know how to extend the function? assume that you have a bump function, the one that I draw. So let's say 0 and then goes to 1. Like this. What can you do with that bump function and the function f? You can multiply them, right? And that will give you a smooth function. The problem is, well, yeah, on this side you don't get f, but on this side you will be extending your function. So this has to do with with this fact. Like this. Okay. Y ya llegó Daniel por ahí. Okay. Well, so this is for just for functions. I didn't. Have you noticed from the beginning? I didn't wrote a proof of this. We just work out this. Now, I want you to understand this proposition very well. This is an exact sequence in cohomology for every k. We only discussed briefly the proof in k equals to 0. More or less the same obstacle that you face in k equals 0 work for any other k. Because basically a k form is a function. Not a real value function, but a function on the same u, m, or v. Okay? Well, so we will use this in the following way. Now, in this case, I wrote down everything regarding what we have seen, all of the exact sequence, n minus 1, 1, and 0. Those n plus 1 rows are exact sequence, right? In this case, we have a huge collection of infinite dimensional vector spaces, like this. Now, I don't know if from algebraic topology, you know what follows next. So like this, they are independent sequences. I have n plus 1 independent sequences, but it follows that they are related because you have in the vertical direction the differential. So using the differential, now all of those n+1 exact sequences are related by using the exterior derivative, TD. So they are not isolated, they are related one to the next one by the differential. Now I'm not writing nothing above, because remember that it is an n-dimensional, so here everything goes to 0. So that's why I didn't write down anything whatsoever. So actually it ends there. And the same on the bottom, because we are already on degree 0. So there's nothing here. Now, this diagram remembers you of something? So here we have only differential forms. We don't have cohomology, and cohomology is our goal. The goal is to compute cohomology. Now, the way that cohomology enters is on the vertical lines, because that's the D. So, by a result of linear algebra or algebraic topology, which is called the, no, it's not the Phi lemma. But all of this induces a single exact sequence in cohomology. And that's the major Vittori sequence. Let me try to fit everything here. Yes. Okay. So what we were aiming at is precisely this exact sequence. Like this. We start on degree 0 and we move forward on degree 0, 1, 2, up to n. And this exact sequence is induced by this diagram. Okay? So, first of all, now this map is the same map in cohomology. I have a closed form, and it's the same one that we had before. The other map, again, it is the same one. Remember, it was restriction. Okay. The only map that it is missing in there that we haven't seen is the map that goes like this. From here This one. That's the map that we haven't seen. Okay? But the other maps, you know exactly what they are. We are only missing the long arrows. What is that function? Any comment or question on this? Okay. So let me have this right. So this is an exact sequence, and we will use this exact sequence to compute the cohomology of several manifolds. The way that it is used, it works in many directions. The most straightforward is you know the cohomology of U, of V, and the intersection, and then you can compute the cohomology of the manifold. But there are even some cases when it is not used like that. Sometimes you know the cohomology of the manifold, of the intersection of V, and you want to compute the cohomology of this open set. That's also something that we frequently use. Okay? Any questions up to this point? Great. For the time being, I'm not going to prove this. We will do it later, but right now my interest is that you learn how to use this machinery. That's right now what I'm going to focus. To prove this relies on this grid that we have here. And basically, the only thing that we need is, what I want to say, this is not something related to the RAM cohomology. It is related on having exact sequences like this, on the rows exact sequences, and you have a differential, the red map. A differential that, remember, d squared is 0. Having that, you will have the long exact sequence. So we will prove this in detail. Let me just show you in arrows what is this function. So here, take an element that it is closed. Okay? Because it is closed, that means that when you go up, it goes to 0. Because the red arrow is the differential. Now, because the row is exact, you have an element here and an element here that map to that, right? Because it is exact. Well, now, whatever you have here, apply the differential to get something here and get something here. It happens that this square commutes. That means that whatever you have here maps to 0. And because the sequence is exact, you get an element here. And that's the corresponding element of the map. Okay, so the red arrows are fundamental. Great. Any questions or comments? Well, let's compute the cohomology of the circle using the Meyer-Viettori sequence. I don't know what happened here. Let's see. Okay, so I have the cohomology of the circle. We need to take two open sets that cover the whole manifold. Okay? That's like the input. So let's do that. I'm going to take this to be U, something that goes, well, not that important. And I'm going to take V, something like this. Okay? They are open sets, and the union is the whole circle. What can you say about U? Remember that they are open, right? They are open on the circle. What can you say about the open set U? Salvador, Moisés. I mean, remember, well, let me change it. Maybe you will be more happy if I do it this way. Because you know this very well. So let me change the U. U is all of the circle except one point. Let's remove the south pole. And this is U. And the same for V. I'm going to remove the north pole. And this is V. So now, can you answer that?
They're both diffeomorphic to a line.
Right. Stereographic projection, and they are diffeomorphic to a line. So this is P, and this is Q. Do you agree, Moises?
Yes.
And now, well, before that, what about U intersection V? What can you say about that?
They will remove the zero.
Wait, wait. So in terms of equality, that's true. So this is the circle minus 2 points. And this is diffeomorphic to what?
Whatever minus a point.
Okay, I agree with that. Yes. Let's say the origin. But again, the real line minus a point is diffeomorphic to 2 copies of the reals, right? Disjoint, 2 disjoint reals. Okay? Great. Now, so the good thing is that you know what this is now. What is the cohomology of U and V? That's what we computed at the beginning, right? The cohomology of the real line. Now, what about the cohomology of U intersection V? Which is diffeomorphic to the cohomology of 2 disjoint copies of the reals. What is that? I mean, you have a manifold that is not connected. You have 2 components. So basically, one component doesn't see the other component, so this is separately. Right? You have a differential form on a manifold that is not connected, so it's the same as taking a differential form here and a differential form here. There's no interaction between the two because the manifold is not connected. You have 2 components. Okay, so then what is the answer here? And this is what you answer at the beginning, because you have 2 components. Okay? So, for U, V, and the intersection, we know the cohomology. And let's put all of this together. You get the measure vectorial sequence and try to compute the cohomology of the circle. So, Let's write it like this. I'm going to put 2, but we know that there's nothing there. It's only in 1 and in 0. Right? This is of U is R and of V is R. This is something that we're well, I'm sorry, we know this one. What is that one? The circle is connected. So H0 of the circle is the rails. Right, and now U intersection V is something that we just computed, like this. And then here we got 0 plus 0. And then here we got 0. So the Mayer-Vectoric sequence is exactly this. I'm just going to rewrite it like this. That's the Mayer-Vectoric sequence for the circle. And we are missing only one information here. And this is the whole goal of the problem. We need to find that vector space. Any ideas on how to compute that? How can we compute that vector space? Moises? Okay. So this is interesting because, I mean, let's see what else. Let me use this. Remember, well, this map we know because it's the 0 map. We know this map and we know this map. This and this. The long map is the one that we don't know. So it is a mystery what this map is. But even though we don't know what is that linear map, you will be able to compute the cohomology of the circle. And you have to use one of the homework problems that I just mentioned a while ago when we saw exact sequences. That one. Okay? We use that observation, that homework problem, and Daniel is happy about it. He's clapping. Because you see, by the Mayer-Vectoric sequence, we know that that sequence of vector spaces is exact. And we are only missing one vector space. So using that equation, you can compute the dimension of that. So by the exactness of the sequence, what is the dimension of this vector space?
1.
1, exactly. Okay, so now you know the cohomology of the circle. Now, we have the following that we need to understand very well. So, okay, you know that this is isomorphic, sorry, this one is isomorphic to the reals, is one-dimensional. And that's fair, but still, we know what that vector space is, but for instance, we don't have the whole information. For instance, it would be important to know what is the closed one form that generates that vector space. So that's like having even more information about the cohomology. We know that it is one-dimensional, that's fair, but we can even go further and try to understand and to build the one form that generates that vector space. Okay, so at least this is something that I wanted to show you. How can you use the Mayer-Vettori sequence to compute the cohomology of the circle? We will use it to compute other examples. Okay? But we need to learn we need further information, which is related to topology. Basically, I don't know if you've covered this, but we will, don't worry about it. Deformation retraction, or spaces that are homotopy equivalent. Because those spaces can look very strange, but they might have the cohomology of something very simple. Okay? So we will need those concepts, homotopy equivalence, deformation retraction, and together with the Mayer-Vettori sequence, we will compute the cohomology of many, many things. Any questions or comments?
We said that the cohomology of the circle for k equals 0 was R because of connectedness.
Yes, right, yeah. Yes, this one here, we use the fact that R is connected, that the circle is connected, and that's why we put R there, and this one is missing. Any other question? Well, now I want to we still need more to compute the cohomology of the spheres. Because so far we only computed the cohomology of the circle. But let's go up in dimension, okay? The sphere. Based on the previous example, what do you think it will be the U and V that generalize the previous example? Say you want to compute the cohomology of the sphere and you want to use the major vectoric sequence. What is
Again, taking two covers with each one with a point.
But two covers, but what is U?
Like the entire sphere minus 0, 0, minus 1.
Right. So you can also make the entire sphere minus the North Pole and minus the South Pole. Right? And you know that very well. That will give you, again, stereographic projection. And you will have R2. But let's take a cap. That it goes a little bit beyond the equator. And the same down. Now, U and V are diffeomorphic to what? Because U and V are an open disk, right? Now, what can you say about the intersection? For now, I would like to put it explicitly. I would like to think about this in our tree. So it is on the sphere, right? But let's say that the y-axis, the z-axis is between in a small epsilon bar, right? Okay. In terms of the geometry, what is U intersection V? So it is a cylinder, right? If you intersect the two hemispheres, you get a cylinder. Okay, up to this point, everything is correct. Now, of course, we don't know the cohomology of U and V and U intersection V. We will deal with that later. Right now, I just want you to understand UV and the intersection. Very nice. Now, if you do this on S3, what you will get? instead of taking S2, take S3 in R4 if you want. So again, you will take the northern hemisphere and a little bit more to go beyond the equator. V to be the southern hemisphere. You go a little bit above the equator. And then you do the intersection. So everything makes sense? A ver, Daniel está preguntando. Right, yes, Daniel, but right now I decided to not to do that, so that I want to focus on this. If I remove the poles, then I will have to change this. ¿Qué pasó aquí? No le cambié acá, perdón. Se cambió todo. Ya. So that will be, if I take U to be the entire sphere minus the point and also V, we can do it using stereographic projection. As we did for the circle, you will have that. Okay, great. Now, again, take U and V. If you want to be explicit, again, you can write down x1 up to x4. Like this. In the splitting notation, that's the U that we took before. So U intersection V is the same, but x4 will go like this. Okay. Now, the reason that I'm doing this is because I want you to keep this in mind. If you shrink the interval minus epsilon epsilon here, I forgot a square here. Right. If you shrink the interval minus epsilon epsilon, what happens? This is 0 and you get the circle. So you lower in one-dimensional. If you do the same here on this intersection, if you shrink this interval, until it is 0, this is 0, and you get only the 2 sphere. Right? Because the whole idea on any sphere is the equator is a sphere in 1 dimension lower. So for S3, an equator is a 2-dimensional sphere. So for S7, the equator is S6, and so on. So this is something that we will use when we compute the cohomology. Because here, remember, we don't know the cohomology of R2 and of U intersection V. What is going to happen is that U intersection V will have the cohomology of the equator, which is the circle, and we already computed that. And that's why we will proceed. The same for the S3. Once that we computed the cohomology of S2, we will be able to compute the cohomology of S3, because the intersection will have the cohomology of S2. So this is the whole idea right now that I wanted to stress, forgetting about the cohomology, just to understand how the underlying open sets U, V, and the intersection relate to previous results. Okay, so, and again, just to repeat what Salvador and Daniel said, if U is the whole sphere minus the poles, I have this, and this also works. The two sphere without the north and south poles, everything can be shrink to the equator. So that also works. Any questions? So we still need more theory to compute the cohomology of the sphere, but we are there. We are almost getting there. So we need to justify why the cohomology of this is the same as the cohomology of the circle. And for this, again, we use a topology fact. R2 is contractible. And that will help us to know this cohomology, this, and then we will proceed to compute the cohomology of the sphere using the Mayer-Vietoris sequence. Right. Well, if there are no further questions, we will continue next week. No?